Chapter 7. Bipolar junction transistors. Objectives. 1. Analyze BJT band diagrams and understand current gain, base, transport factor, and emitter injection efficiency. 2. Discuss the Ebers-Moll coupled diode model, equivalent circuits, cutoff, saturation, and active regions. 3. Develop the Gummel-Poon charge control model for second order. Effects: early effect, high-level injection. 4. Study HBTs and other advanced BJTs. We begin this chapter with a qualitative discussion of charge transport in a bipolar junction transistor, BJT, to establish a sound physical understanding of its operation. Then we shall investigate carefully the charge distributions in the transistor and relate the three terminal currents to the physical characteristics of the device. Our aim is to gain a solid understanding of the current flow and control of the transistor and to discover the most important secondary effects that influence its operation. We shall discuss the properties of the transistor with proper biasing for amplification and then consider the effects of more general biasing, as encountered in switching circuits. In this chapter we shall use the PNP transistor for most illustrations. The main advantage of the PNP for discussing transistor action is that whole flow and current are in the same direction. This makes the various mechanisms of charge transport somewhat easier to visualize in a preliminary explanation. Once these basic ideas are established for the PNP device, it is simple to relate them to the more widely used transistor, the NPN. The bipolar transistor is basically a simple device, and this section is devoted to a simple and largely qualitative view of BJT operation. We will deal with the details of these transistors in the following sections, but first we must define some terms and gain physical understanding of how carriers are transported through the device. Then we can discuss how the current through two terminals can be controlled by small changes in the current at a third terminal. Figure 7.1 External control of the current in a reverse-biased PN junction. A. Optical generation. B. Junction current voltage characteristics as a function of electron-hole pair generation. C. Minority carrier injection by a hypothetical device. Let us begin the discussion of bipolar transistors by considering the reverse-biased PN junction diode of Fig. 7.1. According to the theory of Chapter 5, the reverse saturation current through this diode depends on the rate at which minority carriers are generated in the neighborhood of the junction. We found, for example, that the reverse current due to holes being swept from N to P is essentially independent of the size of the junction E field and hence is independent of the reverse bias. The reason given was that the hole current depends on how often minority holes are generated by electron-hole pairs creation within a diffusion length of the junction, not upon how fast a particular hole is swept across the depletion layer by the field. As a result, it is possible to increase the reverse current through the diode by increasing the rate of electron-hole pair generation, Fig. 7.1b. One convenient method for accomplishing this is optical excitation of electron-hole pairs with light. Photon energy is greater than energy gap, as in section 4.3. With steady photoexcitation the reverse current will still be essentially independent of bias voltage, and if the dark saturation current is negligible, the reverse current is directly proportional to the optical generation rate GOP. The example of external control of current through a junction by optical generation raises an interesting question. Is it possible to inject minority carriers into the neighborhood of the junction electrically instead of optically? If so, we could control the junction reverse current simply by varying the rate of minority carrier injection. For example, let us consider a hypothetical hole injection device as in Fig. 7.1c. If we can inject holes at a predetermined rate into the N side of the junction, the effect on the junction current will resemble the effects of optical generation. The current from N to P will depend on the hole injection rate and will be essentially independent of the bias voltage. There are several obvious advantages to such an external control of a current. For example, the current through the reverse biased junction would vary very little if the load resistor RL were changed, since the magnitude of the junction voltage is relatively unimportant. Therefore, such an arrangement should be a good approximation to a controllable constant current source. A convenient hole injection device is a forward-biased P+, N junction. According to section 5.3.2, the current in such a junction is due primarily to holes injected from the P+ region into the N material. If we make the N side of the forward-biased junction the same as the N side of the reverse-biased junction, the P+, NP structure of Fig 7.2 results. Figure 7.2 A PNP transistor, A. Schematic representation of a PNP device with a forward-biased emitter junction and a reverse-biased collector junction, B. Current voltage characteristics of the reverse-biased NP junction as a function of emitter current. With this configuration, injection of holes from the P+, N junction into the center N region supplies the minority carrier holes to participate in the reverse current through the NP junction. Of course, it is important that the injected holes do not recombine in the N region before they can diffuse to the depletion layer of the reverse-biased junction. Thus we must make the N region narrow compared with a hole diffusion length. The structure we have described is a PNP-BJT. The forward-biased junction that injects holes into the center N region is called the emitter junction, and the reverse-biased junction that collects the injected holes is called the collector junction. The P+ region, which serves as the source of injected holes, is called the emitter, and the P region into which the holes are swept by the reverse-biased junction is called the collector. The center N region is called the base, for reasons which will become clear in section 7.3, when we discuss the historical development of transistor fabrication. The biasing arrangement in Fig 7.2 is called the common base configuration, since the base electrode B is common to the emitter and collector circuits. To have a good PNP transistor, we would prefer that almost all the holes injected by the emitter into the base be collected. Thus the N-type base region should be narrow, and the whole lifetime TP should be long. This requirement is summed up by specifying WB/LP, where WB is the length of the neutral N material of the base, measured between the depletion regions of the emitter and collector junctions, and LP is the diffusion length for holes in the base square root of diffusion coefficient multiplied by carrier lifespan. With this requirement satisfied, an average hole injected at the emitter junction will diffuse to the depletion region of the collector junction without recombination in the base. A second requirement is that the current emitter current crossing the emitter junction should be composed almost entirely of holes injected into the base, rather than electrons crossing from base to emitter. This requirement is satisfied by doping the base region lightly compared with the emitter, so that the P+, N emitter junction of Fig 7.2 results. Figure 7.3 Summary of hole and electron flow in a PNP transistor with proper biasing. 1. Injected holes lost to recombination in the base. 2. Holes reaching the reverse-biased collector junction. 3. Thermally generated electrons and holes making up the reverse saturation current of the collector junction. 4. Electrons supplied by the base contact for recombination with holes. 5. Electrons injected across the forward-biased emitter junction. It is clear that current IE flows into the emitter of a properly biased PNP transistor and that IC flows out at the collector, since the direction of hole flow is from the emitter to collector. However, the base current IB requires a bit more thought. In a good transistor the base current will be very small since emitter current is essentially hole current, and the collected hole current IC is almost equal to IE. There must be some base current, however, due to requirements of electron flow into the N-type base region, Fig 7.3. We can account for IB physically by three dominant mechanisms. A. There must be some recombination of injected holes with electrons in the base, even with WB/LP. The electrons lost to recombination must be resupplied through the base contact. B. Some electrons will be injected from N to P in the forward-biased emitter junction, even if the emitter is heavily doped compared with the base. These electrons must also be supplied by IB. C. Some electrons are swept into the base at the reverse-biased collector junction due to thermal generation in the collector. This small current reduces IB by supplying electrons to the base. The dominant sources of the base current are, A. Recombination in the base and, B. Injection into the emitter region. Both of these effects can be greatly reduced by device design, as we shall see. In a well-designed transistor, IB will be a very small fraction, perhaps 1/100th, of IE. In an NPN transistor the three current directions are reversed, since electrons flow from the emitter to collector and holes must be supplied to the base. The physical mechanisms for operation of the NPN can be understood simply by reversing the roles of electrons and holes in the PNP discussion. In this section we shall discuss rather simply the various factors involved in transistor amplification. Basically, the transistor is useful in amplifiers because the currents at the emitter and collector are controllable by the relatively small base current. The essential mechanisms are easy to understand if various secondary effects are neglected. We shall use total current, DC plus AC, in this discussion, with the understanding that the simple analysis applies only to DC and to small signal AC at low frequencies. We can relate the terminal currents of the transistor IE, IB, and IC by several important factors. In this introduction we shall neglect the saturation current at the collector, Fig 7.3, component 3, and such effects as recombination in the transition regions. Under these assumptions, the collector current is made up entirely of those holes injected at the emitter, which are not lost to recombination in the base. Thus IC is proportional to the hole component of the emitter current IEP. The proportionality factor B is simply the fraction of injected holes which make it across the base to the collector. B is called the base transport factor. The total emitter current IE is made up of the hole component IEP and the electron component IEN, due to electrons injected from the base to emitter, component 5 in Fig 7.3. The emitter injection efficiency G is. For an efficient transistor we would like B and G to be very near unity, that is, the emitter current should be due mostly to holes, G equal 1, and most of the injected holes should eventually participate in the collector current. B equal 1. The relation between the collector and emitter currents is. The product BG is defined as the factor A, called the current transfer ratio, which represents the emitter to collector current amplification. There is no real amplification between these currents, since A is smaller than unity. On the other hand, the relation between IC and IB is more promising for amplification. In accounting for the base current, we must include the rates at which electrons are lost from the base by injection across the emitter junction, IEN, and the rate of electron recombination with holes in the base. In each case, the lost electrons must be resupplied through the base current IB. If the fraction of injected holes making it across the base without recombination is B, it follows that 1B is the fraction recombining in the base. Thus the base current is. Neglecting the collector saturation current. The relation between the collector and base currents is found from EQs 7.1 and 7.4. The factor B relating the collector current to the base current is the base to collector current amplification factor 1. Since A is near unity, it is clear that B can be large for a good transistor, and the collector current is large compared with the base current. It remains to be shown that the collector current IC can be controlled by variations in the small current IB. In the discussion to this point, we have indicated control of IC by the emitter current IE, with the base current characterized as a small side effect. In fact, we can show from space charge neutrality arguments that IB can indeed be used to determine the magnitude of IC. Let us consider the transistor of Fig 7.4, in which IB is determined by a biasing circuit. For simplicity, we shall assume unity emitter injection efficiency and negligible collector saturation current. Since the N-type base region is electrostatically neutral between the two transition regions, the presence of excess holes in transit from emitter to collector calls for compensating excess electrons from the base contact. Figure 7.4 example of amplification in a common emitter transistor circuit. A. Biasing circuit. B. Addition of an AC variation of base current IB to the DC value of IB, resulting in an AC component IC. However, there is an important difference in the times that electrons and holes spend in the base. The average excess hole spends a time Tt, defined as the transit time from the emitter to collector. Since the base width Wb is made small compared with Lp, this transit time is much less than the average whole lifetime Tp in the base 2. On the other hand, an average excess electron supplied from the base contact spends Tp seconds in the base, supplying space charge neutrality during the lifetime of an average excess hole. While the average electron waits Tp seconds for recombination, many individual holes can enter and leave the base region, each with an average transit time Tt. In particular, for each electron entering from the base contact, Tp-Tt holes can pass from the emitter to collector while maintaining space charge neutrality. Thus the ratio of collector current to base current is simply for G=1 and negligible collector saturation current. If the electron supply to the base, Ib, is restricted, the traffic of holes from the emitter to base is correspondingly reduced. This can be argued simply by supposing that the hole injection does continue despite the restriction on electrons from the base contact. The result would be a net buildup of positive charge in the base and a loss of forward bias, and therefore a loss of hole injection, at the emitter junction. Clearly, the supply of electrons through Ib can be used to raise or lower the hole flow from emitter to collector. The base current is controlled independently in Fig. 7.4. This is called a common emitter circuit, since the emitter electrode is common to the base and collector circuits. The emitter junction is clearly forward biased by the battery in the base circuit. The voltage drop in the forward biased emitter junction is small, however, so that almost all of the voltage from the collector to emitter appears across the reverse biased collector junction. Since VBE is small for the forward biased junction, we can neglect it and approximate the base current as 5 volts divided by 50 kilo ohms equals 0.1 milliamps. If Tp equal 10 microseconds and Tt equals 0.1 microseconds, B for the transistor is 100 and the collector current IC is 10 milliamps. It is important to note that IC is determined by B and the base current, rather than by the battery and resistor in the collector circuit, as long as these are of reasonable values to maintain a reverse biased collector junction. In this example, 5 volts of the collector circuit battery voltage appears across the 500 ohms resistor, and 5 volts serves to reverse bias the collector junction. If a small AC current IB is superimposed on the steady state base current of Fig. 7.4a, a corresponding AC current IC appears in the collector circuit. The time-varying portion of the collector current will be IB multiplied by the factor B, and current gain results. We have neglected a number of important properties of the transistor in this introductory discussion, and many of these properties will be treated in detail below. We have established, however, the fundamental basis of operation for the bipolar transistor and have indicated in a simplified way how it can be used to produce current gain in an electronic circuit. Show that EQ 7.7 is valid from arguments of the steady state example 7.1 replacement of stored charge. Assume that Tn equal Tp. B. What is the steady state charge Qn equal Qp due to excess electrons and holes in the neutral base region for the transistor of Fig. 7.4, a. In steady state there are excess electrons and holes in the base. The charge in the electron distribution Qn is replaced every Tp seconds. Thus Ib equal coulomb per carrier lifetime. The charge in the hole distribution Qp is collected every Tt seconds, and Ic equal Qp/Tt. For space charge neutrality, Qn equal Qp, and the first transistor invented by Bardeen and Brattain in 1947 was the point contact transistor. In this device 2 sharp metal wires, or cat's whiskers, formed an emitter of carriers and a collector of carriers. These wires were simply pressed onto a slab of germanium which provided a base or mechanical support, through which the injected carriers flowed. This basic invention rapidly led to the BJT, in which charge injection and collection was achieved using 2 p-n junctions in proximity to each other. The p-n junctions in BJTs can be formed in a variety of ways using thermal diffusion, but modern devices are generally made using ion implantation, section 5.1.4. Let us review a simplified version of how to make a double polysilicon, Self-aligned NPN-SI BJT. This is the most commonly used, state-of-the-art technique for making BJTs for use in an IC. Use of NPN transistors is more popular than PNP devices because of the higher mobility of electrons compared with holes. The process steps are shown in cross-sectional view in Fig 7.5. A P-type silicon substrate is oxidized, windows are defined using photolithography and etched in the oxide. Using the photoresist and oxide as an implant mask, a donor with very small diffusivity in silicon, such as arsine or antimony, is implanted into the open window to form a highly conductive N+ layer, Fig 7.5a. Subsequently, the photoresist and the oxide are removed, and a lightly doped N-type epitaxial layer is grown. During this high-temperature growth, the implanted N+ layer diffuses only slightly toward the surface and becomes a conductive buried collector, also called a subcollector. The N+ subcollector layer guarantees a low collector series resistance when it is connected subsequently to the collector ohmic contact, sometimes through the use of an optional, mask deep N+ sinker implant or diffusion only in the collector contact region, Fig 7.5c. The lightly doped N-type collector region above the N+ subcollector in the part of the BJT where the base and emitter are formed ensures a high base collector reverse breakdown voltage. It turns out that wherever the subcollector is formed, and subsequently the epitaxial layer is grown on top, there is a notch or step in the substrate surface. This notch is not explicitly shown in Fig 7.5a. This notch is very useful as a marker of the location of the subcollectors because, subsequently, we have to align the locos isolation mask with respect to the subcollector. For integrated circuits involving not just discrete BJTs, but many interconnected transistors, there are issues involving electrical isolation of adjacent BJTs in order to ensure that there is no electrical crosstalk between them. As described in section 6.4.1, such an isolation can be achieved by locos to form field or isolation oxides after a B-channel stops implant, Fig 7.5b. Another isolation scheme that is particularly well suited for high-density bipolar circuits involves the formation of shallow trenches by reactive ion etching, RE, backfilled with oxide and polysilicon, section 9.3.1. In this process a nitride layer is patterned and used as an etch mask for an anisotropic etch of the silicon to form the trench. Using RE, a narrow trench about 1 mm deep can be formed with very straight side walls. Oxidation inside the trench forms an insulating layer, and the trench is then filled with oxide by low-pressure chemical vapor deposition, LPCVD. A polysilicon layer is deposited by LPCVD, and doped heavily P+ with B either during deposition or subsequently by ion implantation. An oxide layer is deposited next by LPCVD. Using photolithography with the base/emitter mask, a window is etched in the polysilicon/oxide stack by reactive ion etching, Fig 7.5c. A heavily doped extrinsic P+ base is formed by diffusion of B from the doped polysilicon layer into the substrate in order to provide a low resistance, high-speed base ohmic contact. An oxide layer is then deposited by LPCVD, which has the effect of closing up the base window that was etched previously, and B is implanted into this window, Fig 7.5d. This base implant forms a more lightly P-doped intrinsic base through which most of the current flows from the emitter to the collector. The more heavily doped extrinsic base forms a collar around the intrinsic base, and serves to reduce the base series resistance. It is critical that the base be enclosed well within the collector because otherwise it would be shorted to the P substrate. Figure 7.5 Process flow for double polysilicon, self-aligned NPN BJT, A, N+ buried layer formation, B, N epitaxy followed by locos isolation, C, base emitter window definition and, optional, mask sinker implant, P, into collector contact region, D, intrinsic base implant using self-aligned oxide sidewall spacers, E, self-aligned formation of N+ emitter, as well as N+ collector contact. Finally, another LPCVD oxide layer is deposited to close up the base window further, and the oxide is etched all the way to the silicon substrate by reactive ion etching, leaving oxide spacers on the side walls. Heavily N+ doped, typically with arsine, polysilicon is then deposited on the substrate, patterned and etched, forming polysilicon emitter, polyemitter, and collector contacts, as shown in Fig 7.5e. The use of two LPCVD polysilicon layers explains why this process is referred to as the double polysilicon process. Arsenic from the polysilicon is diffused into the substrate to form the N+ emitter region nested within the base in a self-aligned manner, as well as the N+ collector contact. Self-alignment refers to the fact that a separate lithography step is not required to form the N+ emitter region. We cleverly made use of the oxide sidewall spacers to ensure that the N+ emitter region lies within the intrinsic p-type base. This is critical because otherwise the emitter gets shorted to the collector. We also want a gap between the N+ emitter and the P+ extrinsic base, because otherwise the emitter base junction capacitance becomes too high. In the vertical direction, the difference between the emitter base junction and the base collector junction determines the base width. This is made very narrow in high gain, high speed BJTs. Finally, an oxide layer is deposited by CVD. Windows are etched in it corresponding to the emitter, E, base, B, and collector, C, contacts, and a suitable contact metal such as Al is sputter deposited to form the ohmic contacts. The aluminum is patterned photolithographically using the interconnect mask, and etched using reactive ion etching. The many integrated circuits that are made simultaneously on the wafer are then separated into individual dies by sawing, mounted on suitable packages, and the various contacts are wire bonded to the external leads of the package. In this section we examine the operation of a BJT in more detail. We begin our analysis by applying the techniques of previous chapters to the problem of hole injection into a narrow N-type base region. The mathematics is very similar to that used in the problem of the narrow base diode, Prob 5.40. Basically, we assume holes are injected into the base at the forward biased emitter, and these holes diffuse to the collector junction. The first step is to solve for the excess hole distribution in the base, and the second step is to evaluate the emitter and collector currents, i.e., IC, from the gradient of the hole distribution on each side of the base. Then the base current, IB, can be found from a current summation or from a charge control analysis of recombination in the base. We shall at first simplify the calculations by making several assumptions. 1. Holes diffuse from the emitter to collector, drift is negligible in the base region. 2. The emitter current is made up entirely of holes, the emitter injection efficiency is G equal 1. 3. The collector saturation current is negligible. 4. The active part of the base and the two junctions are of uniform cross-sectional area A. Current flow in the base is essentially one-dimensional from the emitter to collector. 5. All currents and voltages are steady state. In later sections we shall consider the implications of imperfect injection efficiency, drift due to non-uniform doping in the base, structural effects such as different areas for the emitter and collector junctions, and capacitance and transit time effects in AC operation. Solution of the diffusion equation in the base region. Since the injected holes are assumed to flow from the emitter to collector by diffusion, we can evaluate the currents crossing the two junctions by techniques used in Chapter 5. Neglecting recombination in the two depletion regions, the hole current entering the base at the emitter junction is the current IE, and the hole current leaving the base at the collector is IC. If we can solve for the distribution of excess holes in the base region, it is simple to evaluate the gradient of the distribution at the two ends of the base to find the currents. We shall consider the simplified geometry of Fig 7.6a, in which the base width is WB between the two depletion regions, and the uniform cross-sectional area is A. In equilibrium, the Fermi level is flat, and the band diagram corresponds to that for two back-to-back PN junctions. But, for a forward-biased emitter and a reverse-biased collector, normal active mode, the Fermi level splits up into quasi-Fermi levels, as shown in Fig 7.6b. the barrier at the emitter base junction is reduced by the forward bias, and that at the collector base junction is increased by the reverse bias. The excess hole concentration at the edge of the emitter depletion region PE and the corresponding concentration on the collector side of the base PC are found from EQ. 529. If the emitter junction is strongly forward biased, emitter base voltage is greater than thermal voltage, and the collector junction is strongly reverse biased, collector base voltage is less than zero, these excess concentrations simplify to. We can solve for the excess hole concentration as a function of distance in the base hole gradient using the proper boundary conditions in the diffusion equation, EQ. 434b. Figure 7.6a, simplified PNP transistor geometry used in the calculations. B, a PNP transistor at equilibrium, flat Fermi level, and with normal active bias. The quasi-Fermi levels are separated by the applied voltage times Q. The solution of this equation is, where Lp is the diffusion length of holes in the base region. Unlike the simple problem of injection into a long N region, we cannot eliminate one of the constants by assuming the excess holes disappear for large Xn. In fact, since Wb is less than Lp in a properly designed transistor, most of the injected holes reach the collector at Wb. The solution is very similar to that of the narrow base diode problem. In this case, the appropriate boundary conditions are. Solving for the parameters C1 and C2, we obtain these parameters applied to EQ. 711, give the full expression for the excess hole distribution in the base region. For example, if we assume that the collector junction is strongly reverse biased EQ. 79b, and the equilibrium hole concentration Pn is negligible compared with the injected concentration Pe, the excess hole distribution simplifies to. The various terms in EQ. 714, are sketched in Fig 77a, and the corresponding excess hole distribution in the base region is demonstrated for a moderate value of Wb is greater than Lp. Note that dp, xn, varies almost linearly between the emitter and collector junction depletion regions. As we shall see, the slight deviation from linearity of the distribution indicates the small value of Ib caused by recombination in the base region. The minority carrier electron concentrations in the emitter and collector corresponding to a forward-biased emitter and reverse-biased collector are shown in Fig 77b. Here, the excess electron concentration in the P+ emitter is shown to decay exponentially to zero, corresponding to a long diode. This is because, at high emitter doping levels, the minority carrier electron diffusion length is often shorter than the thin emitter region. Otherwise, the narrow diode expressions must be used in the emitter region. For polyemitter structures, the carrier concentration profile is more complicated, as discussed later. The exact form of IEN and the emitter injection efficiency will therefore depend on these details. Evaluation of the terminal currents. Having solved for the excess hole distribution in the base region, we can evaluate the emitter and collector currents from the gradient of the hole concentration at each depletion region edge. From EQ. 422b, we have Figure 77a, sketch of the terms in EQ. 714, illustrating the linearity of the hole distribution in the base region. In this example, Wb divided by Lp equal 1 divided by 2 equals 0.5. B. Electron distributions in the emitter and collector. This expression evaluated at xn equals 0 gives the whole component of the emitter current. Similarly, if we neglect the electrons crossing from the collector to base in the collector reverse saturation current, IC is made up entirely of holes entering the collector depletion region from the base. Evaluating EQ. 715, at xn equal Wb we have the collector current. When the parameters C1 and C2 are substituted from EQs. 713, the emitter and collector currents take a form that is most easily written in terms of hyperbolic functions. Now we can obtain the value of IB by a current summation, noting that the sum of the base and collector currents leaving the device must equal the emitter current entering. if IEP for G1. By using the techniques of Chapter 5 we have evaluated the three terminal currents of the transistor in terms of the material parameters, the base width, and the excess concentrations PE and PC. Furthermore, since these excess concentrations are related in a straightforward way to the emitter and collector junction bias voltages by EQ 7-8, it should be simple to evaluate the transistor performance under various biasing conditions. It is important to note here that EQs 718 and 719 are not restricted to the case of the usual transistor biasing. For example, PC may be PN for a strongly reverse biased collector, or it may be a significant positive number if the collector is positively biased. The generality of these equations will be used in section 7.5 in considering the application of transistors to switching circuits. A. Find the expression for the current I for the transistor connection shown if G equal 1. B. How does the current I divide between the base lead and the collector lead? Thus from EQ 718a, where IC and IB are the components in the collector lead and base lead, respectively. Note that these results are analogous to those of probes 5.40 and 5.41 for the narrow base diode. Approximations of the terminal currents. The general equations of the previous section can be simplified for the case of normal transistor biasing, and such a simplification allows us to gain insight into the current flow. For example, if the collector is reverse biased, PC equal PN from EQ 79b. Furthermore, if the equilibrium hole concentration Pn is small, Fig 78a, we can neglect the terms involving PC. For G1, the terminal currents reduce to those of example 7.2. Figure 7.8 approximate excess hole distributions in the base, A, forward biased emitter, reverse biased collector, B, triangular distribution for VCB equals 0 or for negligible Pn. Series expansions of the hyperbolic functions are given in Table 7.1. For small values of WBLP, we can neglect the terms above the first order of the argument. It is clear from this table and EQ 720, that IC is only slightly smaller than IE, as expected. The first order approximation of tan Y is simply Y, so that the base current is. The same approximate expression for the base current is found from the difference in the first order approximations to emitter current and collector current. This expression for IB accounts for recombination in the base region. We must include injection into the emitter in many BJT devices, as discussed in section 7.4.4. If recombination in the base dominates the base current, IB can be obtained from the charge control model, assuming an essentially straight line hole distribution in the base, Fig 7.8b. Since the hole distribution diagram appears as a triangle in this approximation, we have Table 7.1 expansions of several pertinent hyperbolic functions. If we consider that this stored charge must be replaced every Tp seconds and relate the recombination rate to the rate at which electrons are supplied by the base current becomes, which is the same as that found in EQs 721 and 722. Since we have neglected the collector saturation current and have assumed G equal 1 in these approximations, the difference between emitter current and collector current is accounted for by the requirements of recombination in the base. In EQ 724, we have a clear demonstration that the base current is reduced for small Wb and large Tp. We can increase Tp by using light doping in the base region, which of course also improves the emitter injection efficiency. The straight line approximation of the excess hole distribution, Fig 7.8, is fairly accurate in calculating the base current. On the other hand, it does not give a valid picture of IE and IC. If the distribution were perfectly straight, the slope would be the same at each end of the base region. This would imply zero base current, which is not the case. There must be some droop to the distribution, as in the more accurate curve of Fig 7.7. This slight deviation from linearity gives a steeper slope at xn equals 0 than at xn equal Wb, and the value of emitter current is larger than collector current by the amount of base current. The reason we can use the straight line approximation in the charge control calculation of base current is that the area under the whole distribution curve is essentially the same in the two cases. Current transfer ratio. The value of IE calculated thus far in this section is more properly designated EP, since we have assumed that G equal 1, the emitter current due entirely to hole injection. Actually, there is always some electron injection across the forward-biased emitter junction in a real transistor, and this effect is important in calculating the current transfer ratio. As shown in example 7.3, the emitter injection efficiency of a PNP transistor can be written in terms of the emitter and base properties. In this equation we use superscripts to indicate which side of the emitter-base junction is referred to. For example, LNP is the hole diffusion length in the N-type base region and MNP is the electron mobility in the P-type emitter region. In an NPN the superscripts and subscripts would be changed along with the majority carrier symbols. Using EQ 720A for IEP, and EQ 720B for collector current, the base transport factor B is, and the current transfer ratio is the product of B and G as in EQ 7.3. Extend EQ 720A to include the effects of no unity emitter injection. Example 7.3 efficiency, G61. Derive EQ 725 for G. Assume that the emitter region is long compared with an electron diffusion length. Equation 720A is actually IEP. Thus, the total emitter current is. Since we have assumed that the emitter is long compared with the electron diffusion length in the emitter, the long diode expression applies to IEN. On the other hand, for a very narrow emitter width W, LNP would be replaced by W, corresponding to the narrow diode expression. The expressions derived in section 7.4 describe the terminal currents of the transistor, if the device geometry and other factors are consistent with the assumptions. Real transistors may deviate from these approximations, as we shall see in section 7.7. The collector and emitter junctions may differ in area, saturation current, and other parameters, so that the proper description of the terminal currents may be more complicated than EQs 7.18 and 7.19 suggest. For example, if the roles of the emitter and collector are reversed, these equations predict that the behavior of the transistor is symmetrical. Real transistors, on the other hand, are generally not symmetrical between emitter and collector. This is a particularly important consideration when the transistor is not biased in the usual way. We have discussed normal biasing, sometimes called the normal active mode, in which the emitter junction is forward biased and the collector is reverse biased. In some applications, particularly in switching, this normal biasing rule is violated. In these cases it is important to account for the differences in injection and collection properties of the two junctions. In this section we shall develop a generalized approach which accounts for transistor operation in terms of a coupled diode model, valid for all combinations of emitter and collector bias. This model involves four measurable parameters that can be related to the geometry and material properties of the device. Using this model in conjunction with the charge control approach, we can describe the physical operation of a transistor in switching circuits and in other applications. The coupled diode model. If the collector junction of a transistor is forward biased, we cannot neglect PC, instead, we must use a more general hole distribution in the base region. Fig 7.9 illustrates a situation in which the emitter and collector junctions are both forward biased, so that PE and PC are positive numbers. We can handle this situation with EQs 7.18 and 7.19 for the symmetrical transistor. It is interesting to note that these equations can be considered as linear superpositions of the effects of injection by each junction. For example, the straight line hole distribution of Fig 7.9 can be broken into the two components of Fig 7.9b and c. One component, Fig 7.9b, accounts for the holes. injected by the emitter and collected by the collector. We can call the resulting currents, net emitter current and net collector current, the normal mode components, since they are due to injection from emitter to collector. The component of the whole distribution illustrated by Fig 7.9c results in currents IEI and ICI, which describe injection in the inverted mode of injection from collector to emitter. 3. Of course, these inverted components will be negative, since they account for whole flow opposite to our original definitions of emitter current and collector current. For the symmetrical transistor, these various components are described by EQs. 7.18. Defining AK, CADP-LP, CTNH, WB-LP, and BK, CADP-LP, CSCH, WB-LP, we have Figure 7.9 Evaluation of a whole distribution in terms of components due to normal and inverted modes. A. Approximate whole distribution in the base with emitter and collector junctions forward biased. B. Component due to injection and collection in the normal mode. C. Component due to the inverted mode. The four components are combined by linear superposition in EQ. 7.18. Where A equals A positrons and B equals B positrons. We can see from these equations that a linear superposition of the normal and inverted components does give the result we derived previously for the symmetrical transistor. To be more general, however, we must relate the four components of current by factors which allow for asymmetry in the two junctions. For example, the emitter current in the normal mode can be written where IES is the magnitude of the emitter saturation current in the normal mode. Since we specify PC equals 0 in this mode, we imply that VCB equals 0 in EQ. 7.8b. Thus we shall consider IES to be the magnitude of the emitter saturation current with the collector junction short-circuited. Similarly, the collector current in the inverted mode is where ICS is the magnitude of the collector saturation current with VEB equals 0. As before, the minus sign associated with ICI simply means that in the inverted mode holes are injected opposite to the defined direction of IC. The corresponding collected currents for each mode of operation can be written by defining a NUA for each case, where N and AI are the ratios of collected current to injected current in each mode. We notice that in the inverted mode the injected current is ICI and the collected current is IEI. The total current can again be obtained by superposition of the components. These relations were derived by J.J. Ebers and J.L. Moll and are referred to as the Ebers-Moll equations for while the general form is the same as EQs. 7.28, for the symmetrical transistor, these equations allow for variations in IES, ICS, AI, and due to asymmetry between the junctions. Although we shall not prove it here, it is possible to show by reciprocity arguments that even for non-symmetrical transistors, an interesting feature of the Ebers-Moll equations is that IE and IC are described by terms resembling diode relations, IEN and ICI, plus terms that provide coupling between the properties of the emitter and collector, IEI and ICN. This coupled diode property is illustrated by the equivalent circuit of Fig 7.10. In this figure we take advantage of EQ. 7.8, to write the Ebers-Moll equations in the form. It is often useful to relate the terminal currents to each other as well as to the saturation currents. We can eliminate the saturation current from the coupling term in each part of EQs. 7.32. For example, by multiplying EQ 7.32a by n and subtracting the resulting expression from EQ 7.32b, we have. Similarly, the emitter current can be written in terms of the collector current. The terms 1, ANA, ICS and 1, ANA, IES can be abbreviated as ICO and IEO, respectively, where ICO is the magnitude of the collector saturation current with the emitter junction open, IE equals 0, and IEO is the magnitude of the emitter saturation current with the collector junction open. Figure 7.10 an equivalent circuit synthesizing the Ebers-Moll equations. Figure 7:11 equivalent circuits of the transistor in terms of the terminal currents and the open circuit saturation currents. A. Synthesis of EQs. 737, B. Equivalent circuit with normal biasing. C. Collector characteristics with normal biasing. The Ebers-Moll equations then become, and the equivalent circuit is shown in Fig 711a. In this form the equations describe both the emitter and collector currents in terms of a simple diode characteristic plus a current generator proportional to the other current. 4. Example, under normal biasing the equivalent circuit reduces to the form shown in Fig 711b. The collector current is N times the emitter current plus the collector saturation current, as expected. The resulting collector characteristics of the transistor appear as a series of reverse biased diode curves, displaced by increments proportional to the emitter current, Fig 711c. A symmetrical PNP bipolar transistor has the following properties: area equals 0.0001 square centimeters, base width equals 1 micrometer, 100,000 trillion charge carriers in emitter, carrier lifespan 0.1 microseconds, hole mobility in emitter 200 square centimeters per volt seconds. Electron mobility in emitter 700 square centimeters per volt seconds. 1,000 trillion charge carriers in base. Charge carrier lifespan in base 10 microseconds. Electron mobility in base 1300 square centimeters per volt seconds. Hole mobility in base 450 square centimeters per volt seconds. A. Calculate the saturation current IES equal ICS. B. With VEB equal 0.3 volts and VCB equal -40 volts, calculate the base current IB, assuming perfect emitter injection efficiency. C. Calculate the base transport factor B, emitter injection efficiency G, and amplification factor B, assuming that the emitter region is long compared with Ln. Charge control analysis. The charge control approach is useful in analyzing the transistor terminal currents, particularly in AC applications. Considerations of transit time effects and charge storage are revealed easily by this method. Following the techniques of the previous section, we can separate an arbitrary excess hole distribution in the base into the normal and inverted distributions of Fig 7.9. The charge stored in the normal distribution will be called Qn and the charge under the inverted distribution will be called Chi. Then we can evaluate the currents for the normal and inverted modes in terms of these stored charges. For example, the collected current in the normal mode ICN is simply the charge Qn divided by the mean time required for this charge to be collected. This time is the transit time for the normal mode TTN. On the other hand, the emitter current must support not only the rate of charge collection by the collector but also the recombination rate in the base QN-TPN. Here we use a subscript n with the transit time and lifetime in the normal mode in contrast to the inverted mode, to allow for possible asymmetries due to imbalance in the transistor structure. With these definitions, the normal components of current become. Similarly, the inverted components are where the I subscripts on the stored charge and on the transit and recombination times designate the inverted mode. Combining these equations as in EQs 732, we have the terminal currents for general biasing. It is not difficult to show that these equations correspond to the Ebers-Moll relations EQ 734, where the base current in the normal mode supports recombination, and the base to collector current amplification factor Bn takes the form predicted by EQ 77. This expression for Bn is also obtained from n/1, n. Similarly, IBI is Chi/TPI, and the total base current is. This expression for the base current is substantiated by IE, IC from EQ 739. The effects of time dependence of stored charge can be included in these equations by the methods introduced in section 5.5.1. We can include the proper dependencies by adding a rate of change of stored charge to each of the injection currents IEN and ICI. We shall return to these equations in section 7.8, when we discuss the use of transistors at high frequencies. In a switching operation, a transistor is usually controlled in two conduction states, which can be referred to loosely as the on state and the off state. Ideally, a switch should appear as a short circuit when turned on and an open circuit when turned off. Furthermore, it is desirable to switch the device from one state to the other with no lost time in between. Transistors do not fit this ideal description of a switch, but they can serve as a useful approximation. In practical electronic circuits, the two states of a transistor in switching can be seen in the simple common emitter example of Fig 712. In this figure, the collector current IC is controlled by the base current IB over most of the family of characteristic curves. The load line specifies the locus of allowable IC, VCE, points for the circuit, in analogy with Fig 6.2. If IB is such that the operating point lies somewhere between the two endpoints of the load line. Figure 712 simple switching circuit for a transistor in the common emitter configuration, A. Biasing circuit, B. Collector characteristics and load line for the circuit, with cutoff and saturation indicated, C. Operating regimes of a BJT. Fig 712b, the transistor operates in the normal active mode. That is, the emitter junction is forward biased and the collector is reverse biased, with a reasonable value of IB flowing out of the base. On the other hand, if the base current is 0 or negative, the point C is reached at the bottom end of the load line, and the collector current is negligible. This is the off state of the transistor, and the device is said to be operating in the cutoff regime. If the base current is positive and sufficiently large, the device is driven to the saturation regime, marked S. This is the on state of the transistor, in which a large value of IC flows with only a very small voltage drop VCE. As we shall see below, the beginning of the saturation regime corresponds to the loss of reverse bias across the collector junction. In a typical switching operation, the base current swings from positive to negative, thereby driving the device from saturation to cutoff, and vice versa. In this section we shall explore the nature of conduction in the cutoff and saturation regimes. Also we shall investigate the factors affecting the speed with which the transistor can be switched between the two states. The various regions of operation of a BJT are illustrated in Fig 712c. If the emitter junction is forward biased and the collector reverse biased, we have the normal active mode. The opposite gives us the inverted mode of operation. If both junctions are reverse biased, we get cutoff, leading to a very high impedance state of the BJT. If both junctions are forward biased, we have saturation and a low impedance state. Cutoff. If the emitter junction is reverse biased in the cutoff regime, negative IB, we can approximate the excess hole concentrations at the edges of the reverse-biased emitter and collector junctions as, which implies P, xn, equals 0. The excess hole distribution in the base is approximately constant at Pn, with some slope to the distribution at each edge to account for the reverse saturation current in the junctions. The base current IB can be approximated for a symmetrical transistor on a charge storage basis as Tp. In this calculation, a negative excess hole concentration corresponds to generation in the same way that a positive distribution indicates recombination. This expression is also obtained by applying EQ 744 to EQ 719, with an approximation from Table 7.1. Physically, a small saturation current flows from N to P in each reverse biased junction, and this current is supplied by the base current IB, which is negative when flowing into the base of a PNP device according to our definitions. A more general evaluation of the currents can be obtained from the Ebers-Moll equations by applying EQ 744 to EQ 734. If the short-circuit saturation currents IES and ICS are small and N and AI are both near unity, these currents will be negligible and the cutoff regime will closely approximate the off condition of an ideal switch. The equivalent circuit corresponding to EQ 745 is illustrated in Fig 713b. Saturation. The saturation regime begins when the reverse bias across the collector junction is reduced to zero, and it continues as the collector becomes forward biased. The excess hole distribution in this case is illustrated in Fig 7.14. Figure 7.14 excess hole distribution in the base of a saturated transistor, A, the beginning of saturation, B, oversaturation. The device is saturated when PC equals 0, and forward bias of the collector junction, Fig 7.14b, leads to a positive PC, driving the device further into saturation. With the load line fixed by the battery and the 5 kΩ resistor in Fig 7.12, saturation is reached by increasing the base current IB. We can see how a large value of IB leads to saturation by applying the reasoning of charge control to Fig 7.14. Since a certain amount of stored charge is required to accommodate a given IB, and vice versa, an increase in IB calls for an increase in the area under the P, XN, distribution. In Fig 7.14 the device has just reached saturation, and the collector junction is no longer reverse biased. The implication of this condition for the circuit of Fig 7.12 is easy to state. Since the emitter junction is forward biased and the collector junction has zero bias, very little voltage drop appears across the device from the collector to emitter. The magnitude of VCE is only a fraction of a volt. Therefore, almost all of the battery voltage appears across the resistor, and the collector current is approximately 40 volts/5 kΩ equal 8 milliamps. As the device is driven deeper into saturation, Fig 7.14b, the collector current stays essentially constant while the base current increases. In this saturation condition the transistor approximates the on state of an ideal switch. Although the degree of oversaturation, indicated by the shaded area in Fig 7.14b, does not affect the value of IC significantly, it is important in determining the time required to switch the device from one state to the other. For example, from previous experience we expect the turn-off time, from saturation to cutoff, to be longer for larger values of stored charge in the base. We can calculate the various charging and delay times from EQ 743. Detailed calculations are somewhat involved, but we can simplify the problem greatly with approximations of the type used in Chapter 5 for transient effects in PN junctions. The switching cycle. The various mechanisms of a switching cycle are illustrated in Fig 7.15. If the device is originally in the cutoff condition, a step increase of base current to IB causes the whole distribution to increase approximately as illustrated in Fig 7.15b. As in the transient analysis of Chapter 5, we assume for simplicity of calculation that the distribution maintains a simple form in each time interval of the transient. At time Ts the device enters saturation, and the whole distribution reaches its final state at T2. As the stored charge in the base QB increases, there is an increase in the collector current IC. The collector current does not increase beyond its value at the beginning of saturation Ts, however. We can approximate this saturated collector current as IC equal ECC/RL, where ECC is the value of the collector circuit battery and RL is the load resistor, IC equal 8 mA for the example of Fig 7.12. There is an essentially exponential increase in the collector current while QB rises to its value Qs at Ts. This rise time serves as one of the limitations of the transistor in a switching application. Similarly, when the base current is switched negative, for example, to the value IB, the stored charge must be withdrawn from the base before cutoff is reached. Figure 7.15 Switching effects in a common emitter transistor circuit. A. Circuit diagram. B. Approximate hole distributions in the base during switching from cutoff to saturation. C. Base current, stored charge, and collector current during a turn-on and a turn-off transient. While QB is larger than QS, the collector current remains at the value IC, fixed by the battery and resistor. Thus there is a storage delay time TSD after the base current is switched and before IC begins to fall toward zero. After the stored charge is reduced below Qs, IC drops exponentially with the characteristic fall time. Once the stored charge is withdrawn, the base current cannot be maintained any longer at its large negative value and must decay to the small cutoff value described by EQ. 745C. Specifications for switching transistors. We can determine Ts and Tsd by solving for the time-dependent base current, IB, T, given by an expression similar to EQ. 547. We must also not neglect the charging time of the emitter junction capacitance in going from cutoff to saturation. Since the emitter junction is reverse biased in cutoff, it is necessary for the emitter space charge layer to be charged to the forward bias condition before collector current can flow. Therefore, we should include a delay time Td as in Fig 716 to account for this effect. Figure 716 collector current during switching transients, including the delay time required for charging the junction capacitance, definitions of the rise time and fall time. Typical values of Td are given in the specification information of most switching transistors, along with a rise time Tr, defined as the time required for the collector current to rise from 10 to 90% of its final value. A third specification is the fall time Tf required for IC to fall through a similar fraction of its turn-off excursion. The approach we have taken in analyzing the properties of transistors has involved a number of simplifying assumptions. Some of the assumptions must be modified in dealing with practical devices. In this section we investigate some common deviations from the basic theory and indicate situations in which each effect is important. Since the various effects discussed here involve modifications of the more straightforward theory, they are often labeled secondary effects. This does not imply that they are unimportant. In fact, the effects described in this section can dominate the conduction in transistors under certain conditions of device geometry and circuit application. In this section we shall consider the effects of non-uniform doping in the base region of the transistor. In particular, we shall find that graded doping can lead to a drift component of charge transport across the base, adding to the diffusion of carriers from emitter to collector. We shall discuss the effects of large reverse bias on the collector junction, in terms of widening the space charge region about the junction and avalanche multiplication. We shall see that transistor parameters are affected at high current levels by the degree of injection and by heating effects. We shall consider several structural effects that are important in practical devices, such as asymmetry in the areas of the emitter and collector junctions, series resistance between the base contact and the active part of the base region, and non-uniformity of injection at the emitter junction. All these effects are important in understanding the operation of transistors, and proper consideration of their interactions can contribute greatly to the usefulness of practical transistor circuits. Drift in the base region. The assumption of uniform doping in the base breaks down for implanted junction transistors that usually involve an appreciable amount of impurity grading. For example, the implanted transistor of Fig 7.5 has a doping profile similar to that sketched in Fig 7.17. In this example there is a fairly sharp discontinuity in the doping profile, when the donor concentration in the base region becomes smaller than the constant p-type background doping in the collector. Similarly, the emitter is assumed to be a heavily doped, P+, shallow region, providing a second rather sharp boundary for the base. Within the base region itself, however, the net doping concentration, donors minus acceptors equals net doping, varies along a profile that decreases from the emitter edge to the collector edge. The most likely doping distribution in the base is a portion of a Gaussian, see section 5.1.4, however, we can clearly see the effect of an impurity gradient by assuming for simplicity that n, xn, varies exponentially within the base region, Fig 717b. One important result of a graded base region is that a built-in electric field exists from emitter to collector, for a PNP, thereby adding a drift component to the transport of holes across the base. We can demonstrate this effect very simply by considering the required balance of drift and diffusion in the base at equilibrium. If the net donor doping of the base is large enough to allow the usual approximation n, Xn, equal n, Xn, the balance of electron drift and diffusion currents at equilibrium requires. Therefore, the built-in electric field is, for a doping profile n, Xn, that decreases in the positive Xn direction, this field is positive, directed from emitter to collector. Figure 717 graded doping in the base region of a PNP transistor, A, typical doping profile on a semi-log plot, B, approximate exponential distribution of the net donor concentration in the base region on a linear plot. For the example of an exponential doping profile, the electric field E, Xn, turns out to be constant with position in the base. We can represent an exponential distribution as taking the derivative of this distribution and substituting in EQ. 747, we obtain the constant field. Since this field aids the transport of holes across the base region from emitter to collector, the transit time Tt is reduced below that of a comparable uniform base transistor. Similarly, electron transport in an NPN is aided by the built-in field in the base. This shortening of the transit time can be very important in high-frequency devices, section 7.8.2. Another approach for obtaining a built-in field is to vary the alloy composition X, and therefore e.g. in a base made of an alloy such as silicon 1-X germanium X or indium X gallium 1-X arsenide. We will discuss this further in section 7.9. Base narrowing. In the discussion of transistors thus far, we have assumed that the effective base width Wb is essentially independent of the bias voltages applied to the collector and emitter junctions. This assumption is not always valid. For example, the P+ at N at P+ transistor of Fig 718 is affected by the reverse bias applied to the collector. If the base region is lightly doped, the depletion region at the reverse biased collector junction can extend significantly into the N-type base region. As the collector voltage is increased, the space charge layer takes up more of the metallurgical width of the base Lb, and as a result, the effective base width Wb is decreased. This effect is variously called base narrowing, base width modulation, and the Early effect after J.M. Early, who first interpreted it. The effects of base narrowing are apparent in the collector characteristics for the common emitter configuration, Fig 718b. The decrease in Wb causes B to increase. As a result, the collector current IC increases with collector voltage rather than staying constant as predicted from the simple treatment. The slope introduced by the early effect is almost linear with IC, and the common emitter characteristics extrapolate to an intersection with the voltage axis at VA, called the early voltage. For the P+NP+ device of Fig 718 we can approximate the length L of the collector junction depletion region in the N material from EQ. 523b, with V0 replaced by V0, VCB and VCB taken to be large and negative. Figure 718. The effects of base narrowing on the characteristics of a P+NP+ transistor, A, decrease in the effective base width as the reverse bias on the collector junction is increased, B, common emitter characteristics showing the increase in IC with increased collector voltage. The black lines in B indicate the extrapolation of the curves to the early voltage VA. If the reverse bias on the collector junction is increased far enough, it is possible to decrease Wb to the extent that the collector depletion region essentially fills the entire base. In this punch-through condition holes are swept directly from the emitter region to the collector, and transistor action is lost. Punch-through is a breakdown effect that is generally avoided in circuit design. In most cases, however, avalanche breakdown of the collector junction occurs before punch-through is reached. We shall discuss the effects of avalanche multiplication in the following section. In devices with graded base doping, base narrowing is of less importance. For example, if the donor concentration in the base region of a PNP increases with position from the collector to the emitter, the intrusion of the collector space charge region into the base becomes less important with increased bias as more donors are available to accommodate the space charge. Avalanche breakdown. Before punch-through occurs in most transistors, avalanche multiplication at the collector junction becomes important, see section 5.4.2. As Fig 719 indicates, the collector current increases sharply at a well-defined breakdown voltage BVCBO for the common base configuration. For the common emitter case, however, there is a strong influence of carrier multiplication over a fairly broad range of collector voltage. Furthermore, the breakdown voltage in the common emitter case BVCEO is significantly smaller than BVCBO. We can understand these effects by considering breakdown for the condition IE equals 0 in the common base case and for IB equals 0 in the common emitter case. Figure 719 avalanche breakdown in a transistor, A, common base configuration, B, common emitter configuration. These conditions are implied by the O in the subscripts of BVCEO and BVCBO. In each case the terminal current IC is the current entering the collector depletion region multiplied by the factor M including multiplication. Due to impact ionization, EQ 737b becomes, where for M we have used the empirical expression given in EQ 544. For the limiting common base case of IE equals 0, the lowest curve in Fig 719a, IC is simply MICO, and the breakdown voltage is well defined, as in an isolated junction. The term BVCBO signifies the collector junction breakdown voltage in common base with the emitter open. In the common emitter case the situation is somewhat more complicated. Setting IB equals 0, and therefore, IC equal IE in EQ 751, we notice that in this case the collector current increases indefinitely when man approaches unity. By contrast, M must approach infinity in the common base case before BVCBO is reached. Since N is close to unity in most transistors, M need be only slightly larger than unity for EQ 752, to approach breakdown. Avalanche multiplication thus dominates the current in a common emitter transistor well below the breakdown voltage of the isolated collector junction. The sustaining voltage for avalanching in the common emitter case BVCEO is therefore smaller than BVCBO. We can understand physically why multiplication is so important in the common emitter case by considering the effect of M on the base current. When an ionizing collision occurs in the collector junction depletion region, a secondary hole and electron are created. The primary and secondary holes are swept into the collector in a PNP, but the electron is swept into the base by the junction field. Therefore, the supply of electrons to the base is increased, and from our charge control analysis we conclude that hole injection at the emitter must increase to maintain space charge neutrality. This is a regenerative process, in which an increased injection of holes from the emitter causes an increased multiplication current at the collector junction. This in turn increases the rate at which secondary electrons are swept into the base, calling for more hole injection. Because of this regenerative effect, it is easy to understand why the multiplication factor M need be only slightly greater than unity to start the avalanching process. Injection level, thermal effects. In discussions of transistor characteristics we have assumed that A and B are independent of carrier injection level. Actually, the parameters of a practical transistor may vary considerably with injection level, which is determined by the magnitude of IE or IC. For very low injection, the assumption of negligible recombination in the junction depletion regions is invalid, see section 5.6.2. This is particularly important in the case of recombination in the emitter junction, where any recombination tends to degrade the emitter injection efficiency G. Thus we expect that A and B should decrease for low values of IC, causing the curves of the collector characteristics to be spaced more closely for low currents than for higher currents. As IC is increased beyond the low injection level range, A and B increase but fall off again at very high injection. The primary cause of this fall off is the increase of majority carriers at high injection levels, see section 5.6.1. For example, as the concentration of excess holes injected into the base becomes large, the matching excess electron concentration can become greater than the background Nn. This base conductivity modulation effect results in a decrease in G as more electrons are injected across the emitter junction into the emitter region. Large values of IC may be accompanied by significant power dissipation in the transistor and therefore heating of the device. In particular, the product of IC and the collector voltage VBC is a measure of the power dissipated at the collector junction. This dissipation is due to the fact that carriers swept through the collector junction depletion region are given increased kinetic energy, which in turn is given up to the lattice in scattering collisions. It is very important that the transistor be operated in a range such that IC VBC does not exceed the maximum power rating of the device. In devices designed for high power capability, the transistor is mounted on an efficient heat sink, so that thermal energy can be transferred away from the junction. If the temperature of the device is allowed to increase due to power dissipation or thermal environment, the transistor parameters change. The most important parameters dependent on temperature are the carrier lifetimes and diffusion coefficients. In silicon or germanium devices, the lifetime Tp increases with temperature for most cases, due to thermal re-excitation from recombination centers. This increase in Tp tends to increase B for the transistor. On the other hand, the mobility decreases with increasing temperature in the lattice scattering range, varying approximately as 1 divided by square root from T cubed. See Fig 322. Thus from the Einstein relation, we expect dP to decrease as the temperature increases, thereby causing a drop in B due to an increasing transit time Tt. Of these competing processes, the effect of increasing lifetime with temperature usually dominates, and B becomes larger as the device is heated. It is clear from this effect that thermal runaway can occur if the circuit is not designed to prevent it. For example, a large power dissipation in the device can cause an increase in T. This results in a large B and therefore a large IC for a given base current. The large IC causes more collector dissipation and the cycle continues. This type of runaway of the collector current can result in overheating and destruction of the device. Base resistance and emitter crowding. A number of structural effects are important in determining the operation of a transistor. For example, the emitter and collector areas are considerably different in the implanted transistor of Fig 720A. This and most other structural effects can be accounted for by differences in an, AI, and other parameters in the Ebers-Moll model. Several effects caused by the structural arrangement of real transistors deserve special attention, however. One of the most important of these effects is the fact that base current must pass from the active part of the base region to the base contacts B. Thus, to be accurate, we should include a resistance RB in equivalent models for the transistor to account for voltage drops that may occur between B and the active part of the base. Because of RB, it is common to contact the base with the metallization pattern on both sides of the emitter, as in Fig 720C. Figure 720 effects of a base resistance, A, cross-section of an implanted transistor, B, and C, top view, showing emitter and base areas and metallized contacts, D, illustration of base resistance, E, expanded view of distributed resistance in the active part of the base region. If the transistor is designed so that the N-type regions leading from the base to the contacts are large in cross-sectional area, the base resistance RB may be negligible. On the other hand, the distributed resistance RB along the thin base region is almost always important 5 since the width of the base between the emitter and collector is very narrow, this distributed resistance is usually quite high. Therefore, as base current flows from points within the base region toward each end, a voltage drop occurs along RB. In this case the forward bias across the emitter base junction is not uniform, but instead varies with position according to the voltage drop in the distributed base resistance. In particular, the forward bias of the emitter junction is largest at the corner of the emitter region near the base contact. We can see that this is the case by considering the simplified example of Fig 720E. Neglecting variations in the base current along the path from point A to the contact B, the forward bias of the emitter junction above point A is approximately. Actually, the base current is not uniform along the active part of the base region, and the distributed resistance of the base is more complicated than we have indicated. But this example does illustrate the point of non-uniform injection. Whereas the forward bias at A is approximately described by EQ 753, the emitter bias voltage at point D is, which can be significantly closer to the applied voltage VEB. Since the forward bias is largest at the edge of the emitter, it follows that the injection of holes is also greatest there. This effect is called emitter crowding, and it can strongly affect the behavior of the device. The most important result of emitter crowding is that high injection effects described in the previous section can become dominant locally at the corners of the emitter before the overall emitter current is very large. In transistors designed to handle appreciable current, this is a problem which must be dealt with by proper structural design. The most effective approach to the problem of emitter crowding is to distribute the emitter current along a relatively large emitter edge, thereby reducing the current density at any one point. Clearly, what is needed is an emitter region with a large perimeter compared with its area. A likely geometry to accomplish this is a long thin stripe for the emitter, with base contacts on each side, Fig 720b and c. With this geometry, the total emitter current i.e. is spread out along a rather long edge on each side of the stripe. An even better geometry is several emitter stripes, connected electrically by the metallization and separated by interspersing base contacts, Fig 721. Many such thin emitter and base contact fingers can be interlaced to provide for handling large current in a power transistor. This is often called very descriptively an interdigitate geometry. Figure 721, an interdigitate geometry to compensate for the effects of emitter crowding in a power transistor. A. Cross-section. B. Top view of implanted regions. C. Top view with metallized contacts. The metal interconnections are isolated from the device by an oxide layer except where they contact the appropriate base and emitter regions at windows in the oxide. Gummel-Poon model. The Ebers-Moll model runs into problems if a high degree of accuracy is required for very small BJTs, or where second-order effects become important. The Gummel-Poon model, which is a charge control model, incorporates much more physics. We present a simplified version of the model here. As discussed in section 7.7.1, for typical graded doping profiles in the base, there is a built-in electric field that causes drift of minority carriers. In the same direction they are diffusing from the emitter to collector. This forms the starting point for the derivation of the Gummel-Poon model. As mentioned in section 7.7.1, this electric field aids the motion of the minority carriers in the base, so the current can be written as. We can replace the electric field in the base in EQ 755, by the expression in EQ 747, assuming n, xn, equal donors, xn. Where the Einstein relation is used, we recognize the expression in parenthesis as the derivative of the Pn product. We integrate both sides of EQ 757b, from the emitter base junction, 0, to the base collector junction, WB, keeping in mind that the current IEP, flowing from the emitter to the collector, is more or less constant in the narrow base, so that it can be pulled out of the integral. Now, as described in sections 5.2.2 and 5.3.2, the Pn product changes from the equilibrium value to the non-equilibrium expression, where the separation of the Fermi levels is determined by the applied bias across the junction. Applying this to EQ 758, we have assumed a constant hole diffusivity in the base, dP. The integral in the denominator corresponds to the integrated majority carrier charge in the base, and is known as the base Gummel number, QB. In the normal active mode of operation, where the collector base junction is reverse biased, VCB is negative, and the emitter base junction is forward biased, the emitter hole current flowing to the collector, which is the dominant current, becomes. We can similarly write the base electron current flowing back into the emitter as where QE is the integrated majority carrier charge in the emitter, known as the emitter Gummel number. The crux of the Gummel-Poon model is that the currents are expressed in terms of the net integrated charges in the base and emitter regions, and can easily handle non-uniform doping. Also, since we have obtained expressions for IEP and IEN in terms of QB and QE, we can write down BJT parameters such as the emitter injection efficiency GC EQ 72 in terms of the Gummel numbers. We can also modify the Gummel-Poon model to handle several second-order effects such as the early effect and high-level injection in the base, simply by writing the expression for the base Gummel number, QB, more precisely as follows. Where we explicitly account for the fact that the integration limits, the base emitter junction, xn equals 0, and the base collector junction, wb, are bias dependent. This is, of course, the early effect, section 7.7.2. Furthermore, we see that under high-level injection, sections 5.6.1 and 7.7.4, the integrated majority carrier charge becomes greater than the integrated base dopant charge. Clearly, from EQ 761, this will cause the current from the emitter to collector, IEP, to increase less rapidly with emitter base voltage at high biases. Based on what we learned in section 5.6.1 about high-level injection in a diode, the emitter to collector current for high-level injection in the base increases as. On the other hand, because the emitter doping is typically higher than the base doping, one does not see high-level injection effects in the emitter, and the base current injected into the emitter scales as. Hence, for high VEB. This result shows that the common emitter gain decreases at high injection levels due to excess majority carriers in the base. The Gummel-Poon model also accounts for generation recombination effects in the base emitter depletion region at low current levels. As discussed in section 5.6.2, such effects are accounted for by the diode ideality factor, N. Hence the base current injected into the emitter can be written as. On the other hand, the generally large emitter current injected into the base is not likely to be affected by the generation recombination effects. Therefore, thus, for low VEB or low IC, the current gain, the transistor collector current IC and the base current IB are plotted on a semi-log scale as a function of VEB in Fig 722a. This is referred to as a Gummel plot. The current gain B is shown as a function of IC in Fig 722b. We see the dependence of B on IC in the different bias regions, as described by the Gummel-Poon model. At low injection levels B is degraded by poor emitter injection efficiency EQ 767, and at high currents B decreases due to excess majority charge in the base, which degrades G. It can be shown that if one neglects the early effect, i.e., we assume an infinite early voltage, and the drop of B at high current levels, the Gummel-Poon model simplifies to the Ebers-Moll model. Kirk effect. The current gain drops at high collector currents due to yet another mechanism known as the Kirk effect. This involves an effective widening of the neutral base due to modification of the depletion space charge distribution at the reverse biased base collector junction. This is caused by the buildup of mobile carriers due to increased current flow from the emitter to the collector. This is illustrated in Fig 723 for a PNP BJT. Notice that the polarity of these mobile charges adds to the fixed donor charges on the base side of the base collector depletion region, but subtracts from the fixed acceptor charges on the collector side of the junction, Fig 723c. Figure 722 current voltage characteristics of BJTs, A. The Gummel plot of log of collector and base currents as a function of emitter base forward bias, B. DC common emitter current gain equal IC/IB as a function of IC. 4. The intermediate range, we have ideal behavior where both IC and IB increase exponentially with forward bias with ideality factor n equal 1, leading to a current independent gain. For very low forward biases, the generation recombination, GR, current increases IB and the gain drops. For high forward biases, high-level injection effects cause the IC to increase more slowly, N equal to, than IB, and the gain drops as IC-1. Therefore, fewer uncompensated donors, and thus a smaller depletion width, are needed to maintain the reverse voltage VCB across this junction. As a result, the neutral base width increases from WB in Fig 723b to WB in Fig 723c. Also, the depletion region extends more into the collector side. This is tantamount to moving the base collector junction deeper into the collector. This leads to an effective widening of the neutral base region, the Kirk effect, and to a drop of the current gain and an increase of the base transit time. Figure 723 Kirk effect, A, cross-section of PNP BJT, B, space charge distribution in the base collector reverse biased junction for very low currents, C, space charge distribution at the base collector junction for higher current levels. We see that the injected mobile holes, shown in color, add to the space charge of the immobile donors on the base side of the depletion region, but subtract from the space charge of the immobile acceptors on the collector side. This leads to a widening of the neutral base width from WB to WB. The electric field profile in the collector depletion region in the presence of uncompensated dopant charges and mobile carriers, due to the current flow, is given by Poisson's equation, where the mobile carrier charge concentration is given by the last term, and Vd is the drift velocity of the carriers. The voltage across the reverse biased collector base junction, VCB, is related to the electric field profile by assuming that VCB is fixed, and IC increases, the last term in EQ 768 becomes more important with respect to the ionized dopant charges. In Poisson's equation EQ 768, the extra holes injected into the depletion region have the same effect as if the doping level on the base side were increased and that on the collector side decreased. Since the integral of this field with respect to distance is fixed at VCB EQ 769, this implies that the depletion region on the base side collapses. Although we have chosen to illustrate the Kirk effect for a PNP BJT, similar results are obtained for the NPN transistor. Obviously, the treatment is identical except for the polarity of the various charges. From a more detailed analysis, for NPN devices with an N+ subcollector, it can be shown that the base widening can extend at even higher current levels all the way through the lightly doped collector region to the heavily doped buried subcollector. In this section we discuss the properties of bipolar transistors under high-frequency operation. Some of the frequency limitations are junction capacitance, charging times required when excess carrier distributions are altered, and transit time of carriers across the base region. Our aim here is not to attempt a complete analysis of high-frequency operation, but rather to consider the physical basis of the most important effects. Therefore, we shall include the dominant capacitances and charging times and discuss the effects of the transit time on high-frequency devices. Capacitance and charging times. The most obvious frequency limitation of transistors is the presence of junction capacitance at the emitter and collector junctions. We have considered this type of capacitance in Chapter 5, and we can include junction capacitors CJE and CJC in circuit models for the transistor, Fig 724a. If there is some equivalent resistance RB between the base contact and the active part of the base region, we can also include it in the model, along with RC to account for a series collector resistance 6. Clearly, the combinations of RB with K and RC with CJC can introduce important time constants into AC circuit applications of the device. From section 5.5.4 we recall that capacitive effects can arise from the requirements of altering the carrier distributions during time-varying injection. In AC circuits the transistor is usually biased to a certain steady-state operating point characterized by the DC quantities VBE, VCE, IC, IB, and IE, and then AC signals are superimposed upon these steady-state values. We shall call the AC terms VB, Vs, IC, IB, and IE. Total, A at C plus D at C, quantities will be lowercase with capitalized subscripts. Figure 724 models for AC operation. A. Inclusion of base and collector resistances and junction capacitances. B. Hybrid pi model synthesizing EQs. 774, and 775. If a small AC signal is applied to the emitter PN junction along with a DC level, we can show that. We can relate this time-varying excess hole concentration to the stored charge in the base region, and then use EQ. 743, to determine the resulting currents. For simplicity we shall assume the device is biased in the normal active mode and use only QN, T. Assuming an essentially triangular excess hole distribution in the base, EQ. 723, gives. The terms outside the brackets constitute the DC stored charge IBTP. Now that we have a simple relation for the time-dependent stored charge, we can use EQ. 743C, to write the total base current as. As discussed in section 5.5.4, we must be careful about boundary conditions in determining where the stored charges are extracted or reclaimed in a diode. For the emitter-based diode in a BJT, we have a short diode, where EQ 564 is applicable. The result is that only 2/3 of the stored charge is reclaimed. Hence, we obtain the AC component of the base current is where. Thus, as in the case of the simple diode, an AC conductance and capacitance are associated with the emitter-base junction due to charge storage effects. From EQ 743b, we have the quantity Gm is an AC transconductance, which is evaluated at the steady-state value of collector current IC equal Bib. We can synthesize EQs 774 and 775 in an equivalent AC circuit as in Fig 724b. In this equivalent circuit the voltage VB used in the calculations appears inside the device, so that a new applied voltage VB must be used external to RB to refer to the voltage applied between the contacts, and similarly for VCE. This equivalent model is discussed in detail in most electronic circuits texts. It is often called a hybrid pi model. From Fig 724b it is clear that several charging times are important in the AC operation of a transistor. The most important are the time required to charge the emitter and collector depletion regions and the delay time in altering the charge distribution in the base region. Other delay times included in a complete analysis of high-frequency transistors are the transit time through the collector depletion region and the charge storage time in the collector region. If all of these are included in a single delay time Td, we can estimate the upper frequency limit of the device. This is usually defined as the cutoff frequency for the transistor. It is possible to show that feet represents the frequency at which the AC amplification for the device drops to unity. Transit time effects. In high-frequency transistors the ultimate limitation is often the transit time across the base. For example, in a PNP device the time Tt required for holes to diffuse from emitter to collector can determine the maximum frequency of operation for the device. We can calculate Tt for a transistor with normal biasing and G equal 1 from EQ 720, and the relation. Another instructive way of calculating Tt is to consider that the diffusing holes seem to have an average velocity 8v, xn, 9, actually the individual hole motion is completely random, as discussed in section 4.4.1. The hole current IP, xn, is then given by the transit time is. For a triangular distribution as in Fig 7.8b, the diffusion current is almost constant at, and Tt becomes, as before. The average velocity concept should not be pushed too far in the case of diffusion, but it does serve to illustrate the point that a delay time exists between the injection and collection of holes. We can estimate the transit time for a typical device by choosing a value of Wb, say 0.1 mm, 10 to 5 cm. For silicon, a typical number for hole diffusion is about 10 square centimeters per second, then for this transistor Tt equal 5 picoseconds. Approximating the upper frequency limit as 2 ptt, 1, we can use the transistor to about 30 GHz. Actually, this estimate is too optimistic because of other delay times. The transit time can be reduced by making use of field-driven currents in the base. For the implanted transistor of Fig 717, the holes drift in the built-in field from emitter to collector over most of the base region. By increasing the doping gradient in the base, we can reduce the transit time and thereby increase the maximum frequency of the transistor. Webster effect. While the transit time expression EQ 779 is valid for low-level injection, TT is reduced by up to a factor of 2 under high-level injection. This occurs because the majority carrier concentration increases significantly above its equilibrium value in the base, to match the injected minority carrier concentration. Since the minority carrier concentration decreases from the base emitter junction to the base collector junction, see Fig 7.8, so does the majority carrier concentration. This tends to create a diffusion of the majority carriers from emitter to base. Such a majority carrier diffusion would upset the drift-diffusion balance required to maintain a quasi-equilibrium distribution in the base. Therefore, a built-in electric field develops in the base to create an opposing majority carrier drift current. The direction of this induced field then aids the minority carrier transport from the emitter to the collector, reducing the transit time TT in EQ 779. This is known as the Webster effect. It is interesting to note that this effect is similar to the drift field effects in the base region due to non-uniform base doping, section 7.7.1. For the Webster effect, the induced field is not due to non-uniform doping but rather the non-uniform majority carrier concentration induced by carrier injection. High-frequency transistors. The most obvious generality we can make about the fabrication of high-frequency transistors is that the physical size of the device must be kept small. The base width must be narrow to reduce the transit time, and the emitter and collector areas must be small to reduce junction capacitance. Unfortunately, the requirement of small size generally works against the requirements of power rating for the device. Since we usually require a trade-off between frequency and power, the dimensions and other design features of the transistor must be tailored to the specific circuit requirements. On the other hand, many of the fabrication techniques useful for power devices can be adapted to increase the frequency range. For example, the method of interdigitation, Fig 721, provides a means of increasing the useful emitter edge length while keeping the overall emitter area to a minimum. Therefore, some form of interdigitation is generally used in transistors designed for high frequency and reasonable power requirements. Another set of parameters that must be considered in the design of a high-frequency device is the effective resistance associated with each region of the transistor. Since the emitter, base, and collector resistances affect the various RC charging times, it is important to keep them to a minimum. Therefore, the metallization patterns contacting the emitter and base regions must not present significant series resistance. Furthermore, the semiconductor regions themselves must be designed to reduce resistance. For example, the series base resistance RB of an NPN device can be reduced greatly by performing AP plus diffusion between the contact area on the surface and the active part of the base region. Further reduction of base resistance by heavy doping of the base requires the use of a heterojunction, section 7.9, to maintain G at an acceptable value. In silicon, NPN transistors are usually preferred, since the electron mobility and diffusion coefficient are higher than for holes. It is common to fabricate NPN transistors in N-type epitaxial material grown on an N+ substrate. The heavily doped substrate provides a low resistance contact to the collector region, while maintaining low doping in the epitaxial collector material to ensure a high breakdown voltage of the collector junction, see section 7.3. It is important, however, to keep the collector depletion region as small as possible to reduce the transit time of carriers drifting through the collector junction. This can be accomplished by making the lightly doped collector region narrow so that the depletion region under bias extends to the N+ substrate. As described in section 7.3, an N+ polysilicon layer is generally deposited on the top of the single crystal N+ emitter. The reason for this can be understood from Fig 725. If an ohmic contact were formed directly on top of the narrow N+ emitter, the excess minority carrier hole concentration profile would have a steep gradient because the excess minority carrier concentrations are zero at the ohmic contacts. This leads to a large back-injected base current IEP into the emitter and a degraded emitter injection efficiency. The use of a polysilicon emitter causes the hole concentration profile to have a gentler slope near the base emitter junction, thereby leading to an improved G. The steeper slope of the hole concentration profile in the polysilicon emitter simply reflects the fact that the grain boundary defects in polysilicon lead to a shorter diffusion length. Figure 725 excess minority hole concentration profile in the emitter region of an NPN transistor with and without the use of polyemitters. The carrier profile if an ohmic contact is formed directly on the single crystal silicon emitter is shown by the dashed line. In addition to the various parameters of the device itself, the transistor must be packaged properly to avoid parasitic resistance, inductance, or capacitance at high frequencies. We shall not attempt to describe the many techniques for mounting and packaging transistors here, since methods vary greatly among manufacturers. In section 7.4.4 we saw that the emitter injection efficiency of a bipolar transistor is limited by the fact that carriers can flow from the base into the emitter region, over the emitter junction barrier, which is reduced by the forward bias. According to EQ 725, it is necessary to use lightly doped material for the base region and heavily doped material for the emitter to maintain a high value of G and, therefore, A and B. Unfortunately, the requirement of light base doping results in undesirably high base resistance. This resistance is particularly noticeable in transistors with very narrow base regions. Furthermore, degenerate doping can lead to a slight shrinkage of Eg in the emitter as the donor states merge with the conduction band. This can decrease the emitter injection efficiency. Therefore, a more suitable BJT for high frequency would have a heavily doped base and a lightly doped emitter. This is just the opposite of the traditional BJT discussed thus far in this chapter. To accomplish such a radically different transistor design, we need some other mechanism instead of doping to control the relative amount of injection of electrons and holes across the emitter junction. If transistors are made in materials that allow heterojunctions to be used, the emitter injection efficiency can be increased without strict requirements on doping. In Fig. 726, an NPN transistor made in a single material, homojunction, is contrasted with a heterojunction bipolar transistor, HBT, in which the emitter is a wider bandgap semiconductor. It is possible in such a structure for the barrier for electron injection, QVN, to be smaller than the hole barrier, QVP. Since carrier injection varies exponentially with the barrier height, even a small difference in these two barriers can make a very large difference in the transport of electrons and holes across the emitter junction. Neglecting differences in carrier mobilities and other effects, we can approximate the dependence of carrier injection across the emitter as. In this expression, the ratio of electron current into hole current IP crossing the emitter junction is proportional to the ratio of the doping in the emitter NED and the base NBA. In the homojunction BJT, this doping ratio is all we have to work with in designing a useful emitter junction. However, in the HBT there is an additional factor in which the bandgap difference, e.g. between the wide bandgap emitter and the narrow bandgap base, appears in an exponential factor. As a result, a relatively small value of Eg in the exponential term can dominate EQ 780. This allows us to choose the doping terms for lower base resistance and emitter junction capacitance. In particular, we can choose a heavily doped base to reduce the base resistance and a lightly doped emitter to reduce junction capacitance. Figure 726 contrast of carrier injection at the emitter of A homojunction BJT and B, A heterojunction bipolar transistor, HBT. In the forward-biased homojunction emitter, the electron barrier QVN and the hole barrier QVP are the same. In the HBT with a wide bandgap emitter, the electron barrier is smaller than the hole barrier, resulting in the preferential injection of electrons across the emitter junction. The heterojunction shown in Fig 726 has a smooth barrier, without the spike and notch commonly observed for heterojunctions, see Fig 546. It is possible to smooth out such discontinuities in the bands by grading the composition of the ternary or quaternary alloy between the two materials, Fig 727. Clearly, grading out the conduction band spike improves the electron injection by reducing the barrier that electrons must overcome. There are some HBT designs, however, that make use of the spike as a launching ramp to inject hot electrons into the base. Figure 727 silicon germanide graded base in a silicon NPN transistor. The built-in drift field in the conduction band in the base aids electron transport. Materials commonly used in HBTs obviously include the aluminum gallium arsenide/gallium arsenide system because of its wide range of lattice-matched composition. In addition, the indium gallium arsenide phosphide system, including indium 0.53 gallium 0.47 arsenide, grown on indium phosphide, has become popular in HBT design. It is also possible to make HBTs using elemental semiconductor heterostructures such as silicon/silicon 1, X germanium X. In this material system, the bandgap difference e.g. between the silicon emitter and the narrower bandgap silicon 1X germanium X base occurs primarily in the valence band. As a result, a rather small addition of germanium to the base results in higher electron injection efficiency than is possible in homojunction silicon bipolar transistors. If the silicon germanium alloy composition in the base of an NPN is varied such that energy gap decreases slightly from the emitter side to the collector side of the base, a built-in electric field accelerates electrons through the base region, Fig 727. The resulting field-aided base transport is a major advantage of the HBT. Such graded germanium profiles make the structure more manufacturable, because one does not have to worry about a mismatch between the PN junction and the heterojunction. 7.1 A BJT consists of an emitter base, EB, diode connected back-to-back to a collector base, CB, diode. In the normal active mode of operation, the EB junction is forward biased such that carriers injected from the emitter can diffuse across the narrow base and be collected by the reverse biased CB junction. 7.2 The terminal currents can be determined by solving the drift diffusion and continuity equations for a narrow base diode with suitable boundary conditions. The fraction of the total emitter current that is due to injected carriers from emitter to base is the emitter injection efficiency and is made close to unity by doping the emitter much higher than the base. Another elegant way to increase emitter injection efficiency is to use a larger bandgap emitter than in the base, as in heterojunction bipolar transistors, HBT. 7.3 The fraction of the carriers that survives diffusion across the narrow base is the base transport factor, which is made close to unity by making the base width narrow compared with the diffusion length. The product of emitter injection efficiency and base transport factor gives the current transfer ratio, IC/IE, from which one can determine the common emitter current gain, IC/IB. Active devices such as BJTs provide power gain. 7.4 Equivalent circuit models such as Ebers Mol treat the BJT as two coupled back-to-back diodes, in parallel with controlled current sources. These diodes can be forward or reverse biased for switching applications. If they are both forward biased, the BJT is in a low impedance state, saturation. If they are both reverse biased, it is in a high impedance state, cutoff. 7.5 A charge control analysis of BJTs is possible, as for other devices, in terms of the integrated carrier concentration in the base. IC is given by the base charge divided by the base transit time, while IB is the base charge divided by the carrier lifetime, for unity emitter injection efficiency. 7.6 The Gummel-Poon charge control model gives the current components in terms of the integrated base and emitter dopant charges, Gummel numbers. It is more accurate and can handle some second-order effects better than Ebers Mol. 7.7 Second-order effects include IC increase due to neutral base narrowing for increasing CB reverse bias, early effect, current gain drop at high IC, Kirk effect, i.e. crowding at the emitter edges due to series resistance effects, and BJT breakdown at high biases.